All right, so welcome everyone. We've restarted the Symmetry seminars. We have a new co-organizer, Sal, who's actually also currently in Oxford. So actually 3 out of the 4 people are here in Oxford. And it's a great pleasure of Anton Kapustin from Caltech, and he'll talk about higher form symmetries and anomalies on a lattice. So please take it away.
Thank you. So it's a pleasure to speak at this seminar. And I'm going to talk about some recent work uh, of myself with Caltech graduate student Shishong Shu, and also follow up with a postdoc here, Lev Spodinenko. And very similar results were obtained um, um, by Kawagoe and Shirley, but basically at the same time. Well, especially regarding the first paper, which is Shu. Um, and also there's some unpublished work by Thorngren, Chaika, and Geiko on the same subject. So, let me first summarize the whole talk. So you don't get lost, or if you need to switch off in the middle, at least know what's the main message. So I'm motivated by quantum field theory, even though most of the talk is going to be about the lattice. So let me formulate in terms of QFT on this slide, what I'm trying to argue. So first of all, we're going to think about the QFT or quantum lattice model in these spatial dimensions. And first of all, I would like to propose that the 't Hooft anomalies of zero form symmetries are just an aspect of higher group structure, higher form symmetries. Namely, the 't Hooft anomalies arise from the mixing of zero form symmetries and a particular universal U1 deform symmetry. Second, where does high form symmetry comes from? Basically, just from the ability to talk about symmetries localized in regions in space. Also another thing, which is not very clear in the usual approach to quantum to high form symmetries. Well, the usual approach is Euclidean, but if you work in the operator language, then it becomes clear that higher form symmetries are really kinematic. They depend on the Gauss constraints, but not the Hamiltonian. So that sort of explains their robustness. In the Lagrangian or Euclidean approach to QFT, that's a bit hidden because they're, Gauss law constraints and the Hamiltonian are all part of the same thing, of the action. But, in the Hamiltonian approach, they're clearly separate. And finally, just a general overarching message is homotopy theory is absolutely indispensable for thinking about how symmetry plays with locality. And I would like to stress also that what I'm presenting is not at all the final word on the subject. And homotopy theory is, more subtle notions in homotopy theory probably will be useful to fully understand this interplay between symmetry and locality. So, okay, so now, any questions about the summary? Okay, so let me then jump into the talk. So for here, D is also going to dimension of space. So space-time has dimension d+1 if I'm talking about quantum field theory. So that is to conform to the usual terminology in lattice models where, we talk about dimension of space and time is always the same and continuous. So usually when one talks about higher form symmetries, one defines them as invertible topological defects. That approach assumes Euclidean path integral. I'd like to stress this is not a rigorous definition because nobody knows how to define rigorously Euclidean path integral, or maybe not define, but maybe define in the sense of axiomatization. There's no such axiomatization in general. Well, its situation is better in TQFT, in topological quantum field theory, but I'm not talking about topological quantum field theory. I'm going about topological defects in non-topological QFT. But anyway, so the lore is that if you ask what sort of structure they form, this higher for all symmetries together, well, the claim is that when you have d+1 dimensional QFT, then they form a d+1 group. And again, this is a lore, not a theorem, because you cannot, there's no Euclidean definition, so you cannot prove anything. Everything is non-rigorous. It's more like expectation. So in this talk, I'll try to use operator formalism instead. So many of these issues go away, so you can actually be precise. Now, first of all, what is a D+1 group? Even though there's a group in it, it's actually a notion not from group theory, but from homotopy theory. So remind you what a homotopy is. So when you have topological spaces X and Y, and you have two continuous maps, you say in a homotopy is just continuous deformation of one map into the other. So that all intermediate steps are also continuous. And homotopy equivalence between two maps, or homotopy is usually not with the tilde, so F tilde G. Now, and then once this notion of equivalence sort of maps leads to a notion of equivalence of spaces called homotopy equivalence. You say that so two spaces are homotopy equivalent if there exists a map in one direction and the other direction, both continuous, of course, so that their products are homotopy equivalent to identities. So that's sort of the inverse up to homotopy. And this is an equivalence relation, this one. So, and if you spaces in the same equivalence class define a particular homotopy type. And now we can give definition of a D+1 group. This is simply the homotopy type of a connected space, some space X, with following property. First of all, it's connected, so its pi 0 is trivial, and its homotopy groups vanish above dimension D+1. So this is a space up to homotopy with this property. Some people say that it's a D+1 truncated homotopy type. Okay, so the two important things: connected and it's D+1 truncated. So this is maybe a bit strange because why should we call this a group or high group? Sorry, it's just some space up to homotopy. So let's look at special cases. If d equals 0, then in that case, it just means that there's only one non-trivial homotopy group by 1 of x. And there's a theorem which says that if you have a space with only a single non-trivial homotopy group, then it's going to be determined by this group up to homotopy. And there's a name for this homotopy type. It's called KGN. That's one of the possible notations. Of course, G has to be abelian if n is greater than 1. If n is 1, G can be arbitrary. So for any group and choice of n, you have some canonical homotopy type called KGN. So a one group or a group is simply the same as a space of type KG1. So it's homotopy if its fundamental group is G and all other homotopy groups are trivial. And it's a completely well-defined thing. Now, how do you actually make such a space? Well, there are ways. There's a construction. I'll talk about a bit later how it's constructed. So the space is usually called BG. It's some particular space. Well, okay. So really, we only care about homotopy type, but there is a sort of canonical construction of the space called BG. The classifying, another way to call it, the classifying space of principal G bundles. And G here is just abstract group. So if you think it's not a Lie group or anything like that, it's just the group. In other words, any group is here considered with discrete topology. Now, in general, when you just have some concrete space representing a given higher group, that is a given topological space X, a given homotopy type, then you may call it classifying space B curly B Gothic G of this Gothic G.
Do you make any assumption about compactness? Or it can also
The
be
group is abstract, not topological. If you wish, it has discrete topology, so there's nothing. Yeah, so it's purely algebraic setup. Yeah. So from the world of algebra, where you have a group, you just always construct a space called BG. And I'm not going to discuss here at all what happens if you try to give the group itself some topology, like say in case of a Lie group. Now, so what sort of information is contained in the high group? Well, first of all, of course, we have its homotopy groups. If you have a classifying space, you can compute its homotopy groups. And usually the notation is that, you call the P-form symmetry is the P plus first homotopy group. So it's just a notation. So GP, of course, is abelian for P greater than 0, which matches expectations that, P-form symmetries for P greater than 0 are abelian. That's what we expect from the Euclidean path integral. Just stare, by looking at the defects of um, appropriate codimension. There's, of course, further information in the homotopy type, or it wouldn't be interesting. First of all, it's well known from topology that the fundamental group of any space acts on all other homotopy groups. So then if we go along some path and return to the initial point, then something happens. In general, our other loops, maps from spheres sort of map to some other maps. So there's some action of the group on other homotopy groups. And also, that's not all, though. There's also something called Postnikov invariance of the high group. I'll talk about it later, but let me just, for this talk, you might as well assume that the action of G naught on all these other groups is trivial. It's not like, mathematically it's not required, and also actually not required physically, but it is often the case in physical applications. So let me focus on just on the second part, on the Postnikov invariance. Okay, so what do they actually measure? Well, first of all, if they all vanish, then the classifying space just has this type. It's just a product of spaces of type KG01, KG12, and so forth. This shifts simply because of our notational convention, which to conform with physical notation, what's a zero-form symmetry. Just a product homotopy type. In general, when the Postnikov invariants do not vanish, B curly G or B Gothic G is a fibration over BG0. And the fiber is itself a fibration over BG1 and so forth. So this presentation of the classifying space of a high group, or actually any homotopy type, is called its Postnikov tower. So in a particularly simple cases, only two non-trivial homotopy groups are present. Suppose you have some GN and GM. And then there's only one Postnikov invariance, which takes values in degree m plus 2 cohomology of this homotopy type, of the lower one, with values in the group GM. So it makes sense because we assume that m is greater than n, so GM is definitely abelian. So it's like, let's say even more specifically, suppose you just look at the case when there's only G0 and G1, which is actually always the case in two space-time dimensions. There are only zero-form symmetries and one-form symmetries. Then the high group structure is specified once you specify class, this Postnikov class in H degree 3 cohomology of the space BG0 with coefficients in G1. So if you want, you can think about two group as simply a pair of groups, G0 and G1, and this cohomology class. Okay. But that's sort of the most concise statement of what a two group is. But in actual practice, two groups usually do not arise in this way. Well, first of all, the cohomology class, degree 3 cohomology class, pretty strange thing. It's some function of group elements with values in another group with some satisfying some constraint, modulo some equivalence relation, which is quite fairly complicated. So it's not it's the most concise way, but it's not how homotopy types arise in nature. Okay. Another way, but to say another terminology is two group is it's a connected homotopy two type, meaning it's only pi 0 and pi 1 are non-trivial. Sorry, pi 1 and pi 2 are non-trivial. And D plus 1 group is a connected homotopy D plus 1 type, meaning that homotopy groups from the first to D plus first are non-trivial, maybe non-trivial. So anyway, so presentation using this Postnikov invariance is not the most concise, but it's not the most natural. That's not how things usually arise. Okay, so and if you look back at QFT, well, it's not actually very obvious how to read off Postnikov invariance from the properties of topological defects. Well, actually, a better question is how do we even know that properties of topological defects are encoded in some homotopy type, or more specifically, D plus 1 homotopy type? What does homotopy theory have to do with topological defects? No.
Sorry, can I ask a question? Isn't it the Postnikov invariance basically just encoding some fusion rule with the defects? Like, why is it? I mean, it seems like
Yeah, but it's very elaborate rules. Okay, so you need to explain exactly. Well, I mean, first of all, okay, but maybe only a single Postnikov invariance is present. Maybe you can sort of argue it, but first of all, it's not non-trivial question too. But when more than one is present, then you need really to exhibit the homotopy type. There's no concise uh, description using just a tower of this Postnikov invariance. So yeah, so it's still a non-trivial thing even for a single Postnikov invariant. You need to show that the cycle actually merges and that there's no further information. And in practice, it's actually not completely trivial to read it off, to read off this Postnikov invariant. There are many cases where I think it's difficult. You can maybe read off some information, but not the whole thing. It's non-trivial business. Yeah. So I would say there's no proof in the literature, even for the case of a single Postnikov invariant, that is just two non-trivial homotopy groups that allows you to like a prescription how to compute it from knowing topological defects. You can't really do that because without a rigorous definition of what topological defect is, there's cannot be a rigorous prescription, a rigorous proof that it actually works. So now, okay, so well, there are rigorous approaches to quantum field theory. Um, say the old ones using nets of C-star algebras, but actually that still doesn't seem like help because okay, how are we going to get a homotopy type out of some algebraic setup like nets of C-star algebras? How to get topological space out of that?
Can I ask a question?
Yes.
So you said that when there are in the previous slide, you said that this Pastnikov class is captured by some cohomology group. Is it always the case, or is there also sometimes some beyond cohomology cases?
No, that's actually, if you're really dealing with homotopy type, that's all there is.
But in the first slide, you said that the anomaly can also be understood as an instance of a higher group.
Yes.
So what if your anomaly is beyond cohomology, and then you just have some zero form symmetry and some universal D group, as you
Well, I
said?
guess. Well, I mean the anomalies in principle involve all lower groups as well. So yeah, so I think I don't. I say it's all preliminary, so I don't have a complete answer. But it seems to me that, and also I'm discussing lattice models, not QFT. But I think it's still true. You have a homotopy type. It's just that all the anomalies are still encoded in Postnikov invariants, but how that happens, I don't really understand. Okay. But we do expect a higher group.
It seems like the anomaly is not part of the data for D group, right? The anomaly is additional data.
Uh, I don't know. I don't actually. Okay. These groups also may be highly non-trivial, not the most obvious ones. Okay, these groups G0, G1, and so forth. So they may not be the ones which you think about. So um, they might reflect also the anomalies related to non-group cohomology anomalies, other invertible phases. These G's themselves might encode information about how many invertible phases you have in a particular dimension. That is, when I say high form symmetry, I don't mean like, okay, there are, people say that some theory has a higher form symmetry or some particular symmetry. They usually mean that there is you have some explicit abstract group which acts somehow on your system. Okay. But just the fact that you know about this doesn't mean that that's all the symmetries there are, right? Could be some other symmetries which you need to look at. The full symmetry might involve also, for example, invertible topological field theories in dimension lower than the dimension D or D+1. Okay, so I think the statement that this homotopy type describes all the structures, including anomalies, is solid. It's just the question is what are these G's? Okay, GPs. So now, okay, so like the answer is the answer. I had this question: how do you move from some algebraic setup like algebraic QFT to homotopy type? And well, the point is that homotopy type is not something you necessarily construct from topological space. It's not like necessarily topological space up to equivalence of some type. There are many contexts in mathematics where a homotopy type appears, and many of them have nothing to do with topology. Actually, even sometimes, even in logic, mathematical logic, homotopy types appear. So when you look at the literature, the one very popular way to get a homotopy type is to start with a simplicial set. So a simplicial set, if you don't know what it is, it's just a collection of sets labeled by n. Some integer goes from 0 to infinity, and some maps between these sets, and some identities must be satisfied in every dimension, called simplicial identities. One can also say it more concisely, like it's a contravariant functor from the category of finite ordered sets to the category of sets. So this gadget is purely combinatorial, and a special type of simplicial set called Ken complex can model homotopy types of arbitrary CW complexes. So one doesn't need to construct a space, even though one can. But one can extract homotopy types, homotopy groups, and all these Postnikov invariants from some combinatorial object called the Ken complex. So this is the one model. So these kind of complexes are a model for homotopy types. So maybe we should look for not for a topological space within QFT, but for a Ken complex or something like that. Nice. For example, classifying space BG is usually actually constructed not as a space, but as a Ken complex, collection of sets. One lets G of n to be just G to the power n. And then you can construct maps from the group structure of G. And if you want actual space, you can get it. You can apply something called geometric realization functor and get topological space up to, but you don't have to do that. Okay. So you can just work with a simplicial set. Now, so that tries, the natural idea is to look then for simplicial set within QFT. And then maybe that simplicial set would be the, uncalled high group structure of a QFT. Now, actually, there's no natural simplicial set around, even though, I spent some time thinking about that. In other words, it's not a very natural approach within QFT context. And one, indication that it's probably always going to be like that is that there's no simple conditional simplicial set or Kant complex which ensures that its homotopy type is truncated, it vanishes above some, homotopy group vanish above some degree. But that's like one of the most basic properties of the homotopy type attached to quantum field theory. So it's built in because there are no defects of dimension higher than d, it's higher than d. So this is not very natural within simplicial set approach. Should maybe set some other model for homotopy types where it's more natural to impose it. And as I said, there are actually many, even though simplicial sets are the most popular model for homotopy theory, there are many others. So if you look at d equals 0 in quantum mechanics, you have a group described. One group is a group. There's a corresponding simplicial set, but it's not what we usually think about as symmetry of quantum mechanics. So for general dimensions, it's really more natural to look for a group theoretic model for homotopy types. Okay, let's look for such model, and for d equals 1, in the case of two groups, this is essentially unique such group theoretic model called the crossed module of groups. That was introduced by J.H.C. Whitehead in 1940s, I think. So what is it? It's a cross module, just a pair of groups, H and G, a pair of homomorphisms. First of all, from H to G, and second homomorphism from G to automorphisms of H. In other words, the second one just simply means that G acts on H by automorphisms. And there are some constraints. First of all, first I denote the action of G on H by using this H with superscript G to the left of it, just to avoid writing too many parentheses. So then, first constraint is that this homomorphism rho is equivariant with respect to the action of the group. That is, if of course, group G acts on itself with conjugation, and the homomorphism rho intertwines the action of G on H and the action of G on itself. The second one is kind of weird condition called the Pfeiffer condition. So the expression on the left called Pfeiffer commutator. Okay, that is what it is. For any two elements of capital H, you must have this. And if you can understand actually where both of these come from, if you imagine the following simple example, just take H to be a normal subgroup of a group G, and of course G acts on H by conjugation, then you can easily see that these identities are satisfied. So yeah, so just one example allows you to write down all identities, and then you can just generalize them to more general setup. So it's the cross-module groups. Now, how do we read off a homotopy type of this cross module? Well, we need to read off the homotopy groups and the Postnikov class. First of all, what's pi1? Well, pi1 is the co-kernel of rho. So it's you take G and quotient by the image of H. And that makes sense because this identities ensure that the image is always a normal subgroup in G. So if you take quotient, you still get a group. Okay, and the second homotopy groups is the kernel of rho, and it's actually a subgroup of the center of H. In particular, it's abelian. You can see that from second identity. If suppose H1 and H2 are both in the kernel, then rho H1 is trivial, so this becomes an ordinary commutator. So any two elements in the kernel of a rho commute. Okay. And now, finally, we need a Postnikov class. Well, I assume that the action is trivial, which is usually the case for physics applications. But so this Postnikov class, how do you get that? That's a bit tricky. So first, for any element in the co-kernel of rho, that is in pi1, you pick a representative, I call it a section. Then you define the following function from pi1 times pi1 to h. You look at this combination, s of x1 times x of x2 times s of x1 x2 inverse. That you can easily see is in the image of rho. So you can take the inverse of rho. Well, it's not uniquely defined, but you get something. Pick some particular representative, and you get the function. Of course, it has a lot of ambiguity because you have to first of all choose a section, and second, you need to choose which point in the preimage here. Like when you invert rho, it's ambiguous. But you pick some way to fix ambiguities and get this function, and then you construct this weird-looking thing, beta. And you can check that this beta, even though a priori it's a function from pi1, 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 like on 3 arguments with values in capital H. In fact, it takes values in the kernel of rho. It's a little computation you can do. And moreover, even more non-trivially, that actually is a 3K cycle with values in kernel of rho in pi2. And moreover, its cohomology class is independent of all the choices made. So that's pretty hairy computation. So back in May, when I just asked ChatGPT to do it, it failed. So now it's probably better. I haven't tried it more recently, but it takes some thinking. Yeah. So that shows that actually easier to construct two group than actually this Postnikov classes. That's pretty awkward description of the concrete cohomology class. But it works. There's some construction simply because there's a crossed module. Okay, so that's our model for a two group. How do we find one within QFT? Well, first of all, what do we expect? Pi1 is, of course, system dependent. It depends on which QFT you're talking about. It's, after all, supposed to be an ordinary zero-form symmetry. What about one-form symmetry? Well, typically they're just U1. Why is that? Well, if you don't have gauge symmetries, like what sort of one-form symmetry are there? Well, there's one distinguished one-form symmetry simply because you have scalar operators proportional to identity. It's topological because it doesn't matter, where you put identity, on your one-dimensional space. If you look at invertible operators and unitary, you get just U1. So that's a universal one form. It's a typo here. Universal one-form symmetry of a 1 plus 1 dimensional QFT. Yeah, one-form symmetry. Now, it's not completely universal. Well, it's not complete general answer. It's always there, but there may be more one-form symmetries. For example, if in a 1 plus 1D gauge theory, you have Gauss law, which says the electric field is constant. So E that generates another U1. But that's special to U1 gauge theory. Okay. So anyway, so we expect to have first two group with G1 is one U1, trivial action of G0 if you ignore anti-unitary symmetries, and some Postnikov class. Okay, how can we construct it in QFT?
Sorry, can you go back?
Yes.
Hi, Anton. What
Hi.
happens if you add charge conjugation here?
Yeah, I try to avoid all this. Charge conjugation is fine. Charge conjugation doesn't act. It's a unitary symmetry. It still doesn't do anything to U1.
Doesn't it map E to minus E?
Well, yeah, sure. I'm just saying I'm going to focus on this universal to one-form symmetry, not the extra ones which might be present. It's true that
But you do consider the one-form symmetry generated by E.
well, I can, but right now I won't.
Okay, thank you.
Yeah. So yeah, so you'd certainly have a additional. You may have trivial action is not something required by physics either. Yeah, there are many cases when it's not trivial. So when I choose to focus on this canonical one and ignore anti-unitary, then you don't have non-trivial action.
Can you discuss time reversal as a non-trivial action on U1?
That will be anti-unitary symmetry. I avoid talking about these.
Okay.
Yeah. Okay, now what about the Postnikov class? Well, what does it measure? Well,
Can I ask another
well, you
question?
have in general, well, what does it actually mean to have anomaly? So, okay, so let's talk about anomalies. Suppose you have some abstract group, I call it K, so to avoid confusion with the actual higher form symmetries. What do you mean when I say group, K is a symmetry of a QFT. What it means is there's a homomorphism from abstract group to G0, which from my point of view is just pi1 of this homotopy type. Okay. Now I can also think of it topologically because the homomorphism from K to pi1 gives a continuous map from the classifying space of K to classifying space of pi1. To just the statement that homotopy types, homotopy one types, which only have pi1, can be a model group theory. So it can give one or the other is the same thing. Now, so you have cohomology class on B pi 1, and it is a homomorphism from a space BK to, it is a map from BK to B pi 1. So if you pull back this Postnikov class, you get a now cohomology class on K, that is on BK. Still degree 3 with values still in U1. Okay. Now, if you look at 1 plus 1 dimensions, that this is actually the group of possible anomalies of a zero form symmetry. Okay. So it's natural to conjecture that this is precisely the 't Hooft anomaly of K. So from this point of view, the 't Hooft anomaly is simply an aspect of high group symmetry. So there is some high group structure of a QFT, which involves just zero form symmetries and one form symmetries. And let's just focus on the situation when we only have just U1, one form symmetry. And then for any action of a abstract group on a QFT that is for any homomorphism to pi1, you get this class. And I want to interpret it as a 't Hooft anomaly. So yeah, that's all I mean, that 't Hooft anomaly is an aspect of high group symmetry. It just comes from the mixing of zero form symmetry and one form symmetry. Okay. So if you wish, you can just say Postnikov class is the anomaly of zero form symmetry, which I call G0 or pi1.
Sorry, can you hear me?
Yes.
Can I ask a question? Should we regard this U1 universal symmetry as a global symmetry or as a gauge symmetry? Because there is no
Global.
state that, but there
It's a
is no
global
state that was produced.
one form symmetry.
But are there states in Hilbert space that transform non-trivial and rich?
Well, if you
Because
think
there is
about
arrays in Hilbert space.
sure, but I'm not working with Hilbert space. It's a matter of definition, if you wish. The point is that if you think about identity operator, right? So do you want to like quotient by the trivial ones or not? Usually we don't, and it's a good idea because if you do, then you won't see it on the level on this operator level. If you wish, well, U1 of course acts non-trivial on actually on Hilbert space on the vacuum, for example. So if you work in a particular representation of your operator algebra, you naturally have U1 there, right? Because things can act on the vacuum. For example, that's how anomaly appears, sort of in quantum mechanics, central extension, right? So if you work on Hilbert space, you don't need to make any special effort. You have that U1. However, I want to avoid working in a fixed Hilbert space because in quantum field theory, you usually don't have a canonical one. So just work on a paired algebraic approach. And then you have to sort of by hand add this U1, and what it amounts to is just you do remember the phase of scalar operator.
I see. So
Yeah.
any operator transformed on trivial under this symmetry.
Every operator transforms trivial under the symmetry. Yes.
I see.
Every local operator.
But are there line operators that transform on trivially?
No, it's just everything transforms trivially, but it's still there in the sense that it's a matter of definition.
Okay, I see. Okay, thanks.
Okay, so now let's strengthen this. What does actually anomaly measure from this homotopy point of view? Well, you have this classifying space of a two group. In this case, just a fibration with base classifying space of G0, and fiber is a classifying space of this one-form symmetry G1. So this class vanishes if and only if B curly G is a homotopy equivalent to a trivial fibration, just a product. So now so we have suppose this continuous map from BK to BG0, which comes from a homomorphism K to G0. What does beta K measure? Well, if it's non-zero, you cannot actually lift this map F to a map from BK to the classifying space of curly G. If it vanishes, then there is such a lift. So in words, you can interpret it as follows. So what do I mean from the homotopy point of view? What do I mean by saying that is an anomaly? Well, first of all, there are different things you can mean by an action. And when I say an action is a homomorphism from K to G0, it just means I just ignore all this high group structure. So sort of I think of an action of a group or symmetry in a sort of zero-dimensional sense, 0 plus 1 dimensional sense. And an action in a 1 plus 1 dimensional sense would be a two-group morphism, or which is the same basically as a continuous map of classifying spaces. So anomaly then is just abstraction to promoting the naive 0 plus 1 dimensional action to a like true 1 plus 1 dimensional action.
Can you repeat the last sentence?
So when I say when I say that a group acts on a system, we usually, if we ignore all this high group structure, you can say, well, what does it mean? It simply means there's a group homomorphism between groups. And that will be like an action in zero-dimensional sense. But there are a more refined version of an action. For example, in 1 plus 1 dimensional action, for me, would be a map of two groups, respecting sort of the two-group structure, whatever that means. And anomaly is an abstraction from promoting sort of naive 0 plus 1 dimensional action to 1 plus 1 dimensional action. So this is just like a mathematical sort of interpretation of what it means to have ungaugeable symmetry, like the one where it does act, but not in a refined enough way, which consistent with locality. Okay.
I'm sorry, I have a silly question regarding your last argument. Is this about pure abstraction theory? So like I'm thinking about say that I have some SO and I want to defeat that spin, for example, and I have this abstraction measured by the Stefan
You have
this.
fibration. They're just usual abstraction theory. You have a fibration.
Yeah, exactly. This is the same argument, right?
Yeah. You're not saying anything new. Mathematically, it's well known. It's so I interpret this abstraction in physical words. And the physical words is that somehow the high group carries information about locality. When I try to map your abstract group, which you could think was a very, very simple two group, to the actual group, high group of the Q of T, okay? If you constructed such a map, then yeah, you have constructed a local or gaugeable action. But anomaly arises from the fact that we're specifying an action in a more naive way, as an action in the zero-dimensional sense, by ignoring all this high group structure.
I'm a bit lost. When you say action, what exactly acts and what does it act on?
Well, here's my definition. So my definition is this: there's say, suppose in quantum mechanics. In quantum mechanics, you have some, in the most basic level, you just have a group of all unitaries, right? And if you want to be more specific, maybe you have a Hamiltonian too, and you have a group of all unitaries which commute with the Hamiltonian, right? And that is a group which you often just do not know, right? You have some complicated Hamiltonian, who knows how many symmetries it has in that sense. So now when I say say Z2 is a symmetry of this Hamiltonian, it means I construct the homomorphism from abstract Z2 to that group of unitaries commuting with the Hamiltonian. That's what I mean by an action of a group on a system, or a symmetry. And when I say symmetry of the system is Z2, I just mean that constructed some homomorphism.
So it's a homomorphism from what to what? From the symmetry
From
group?
abstract group. When I say this system has U1 symmetry, what does it mean? I constructed a map from U1, which is a very simple group, to some unknowable or maybe like knowable but very complicated group of unitaries commuting with the Hamiltonian of a particular system. There's a concrete unitary for every element of U1, which commutes with the Hamiltonian. So
Can you take the full group that commutes with the Hamiltonian?
yes, but the point is that usually you don't even know what it is, right?
Well, I would just diagonalize the Hamiltonian and put arbitrary phase on each state, on each
Yeah, it would be
item.
nice. You can like define it if you wish, but the point is that you typically don't know what it is, and it's kind of you can formally say what it is. There's some group, but you don't know. You cannot compute any like you cannot compute it, right? Or it's very difficult to compute it. Say when I say look at say a Coulomb problem, first of all, there's a rotational symmetry. Wait, there's also scaling symmetry. Anything else? And then somebody very smartly says, wait, there's Laplace Runge length vector. And then you're like, okay, is there anything else? So that's not a very easy question, right? So when I say that some group like U1 or Z2, which is how we usually say, is a symmetry, we literally you don't mean that's all the symmetry, right? So yeah. So and when I say that, so there are two different notions of symmetries, if you wish. There is a completely local symmetry of a QFT, and that's encoded by this high group. You can define it, but you don't know what it is typically. And then there is say the Z2 is a symmetry of this theory. What does it mean? It means you construct the homomorphism from your Z2 to zero form symmetries. Okay, that's easier to do. Then you can ask, okay, but is it a local symmetry? Well, is it actually in some sense subgroup of this high group symmetry? So is there a map uh, from this group to the higher group, not just its truncation to zero form symmetries? And that is not obvious, and in general is not true. And that's where the anomaly comes from.
But can I ask a question? Maybe I'm not quite understanding the terminology, because normally anomalous symmetries, we would still say they are local symmetries, right? I mean, why do you need this like this like strong notion of locality that seems like it's not compatible with how we normally talk about locality, where you would still say anomalous symmetry is local?
Anomalous symmetry is local in one sense, but not local in another sense, right? So in local in sense, it maps local operators to local operators. That's not the same thing as being gaugeable.
Can you demonstrate it in more detail in quantum mechanics?
In quantum mechanics, it's no, this anomaly is kind of degenerate case. So but one plus one d case may be easier. Okay. So
Well, in 0 + 1, there's still an anomaly, and that's if this is a projective representation of that symmetry.
yeah, but somehow, as I say, it only really makes sense when you go to think about Hilbert space realization, which I kind of don't want to do in general.
Okay, and in 1 + 1?
Well, I'll maybe a bit clearer when discuss 1 + 1d case.
Okay.
So yeah, so I don't want to do quantum field theory. Let's discuss lattice models instead, because I don't really know how to.
I know there was a question in the chat whether this homomorphism needs to be injective.
Well, it doesn't have to be. Although, of course, if it's not, they can just quotient, but
Yeah, by the stuff that's not.
it doesn't give you anything new, really. Yeah. Okay, so let's look at the 1 + 1d lattice system to see how to construct this high group precisely. And again, I'm going to give you some prescription. It's not going to be very obvious as the right thing. Okay, so I'm trying to basically to define a homotopy theoretic interpretation, and then we'll go think about why it should be the way it is. Okay. So you start with the first of all, it's an algebra in this case. Well, in this case, very easy. Just a tensor product, infinite tensor product of matrix algebras, one per each side. And there's notation you do for any finite subset, you can just set a gamma is a product of all these local matrix algebras. And I'm not doing any completion for this talk. It's just going to be a star algebra, not C-star algebra. Purely algebraic setup. And as an important notion of locality preserving automorphism, well, roughly speaking, something which maps local things to local things, but not quite, a bit more constraining than that. A quantum cell automaton is a star automorphism of this algebra which has a finite range, meaning that if you have some observable sitting on side J, so this quantum cell automaton QCA maps this guy sitting on an actual whole interval from J minus R to J plus R. Okay. So there is some R which works for all observables. That's what it means when say we have a QCA. And these guys form a group. And typically when you think about symmetries of a lattice system, we think about it as a homomorphism from an abstract group to this group of QCAs. Okay. Now, people also talk about circuits, or finite depth unitary circuits. That is a special type of QCAs which are built from gates, unitary gates, and the range is again bounded if you want to get a QCA. So this is not quite the same thing because it turns out circuits is just a normal subgroup of QCAs. And for example, in one dimension, well, let's look at the simple case when everything made of qubits or cupids. So that is, you have, suppose you have like this even more generally. Suppose you have matrix algebras all of the same size and whose dimension is the power of a prime. Then this quotient is just a set of integers. It's like this more general theorem of Gross, Nesme, Werner, Vogt about QCAs in one dimension. And the homomorphism, from QCAs to Z, whose kernel is circuits, is called the GNVW index. So, for example, this group is generally by translations, spatial translations. In the case of, when all matrix algebras have this form. Just as an example. Now, by the way, when you have some homomorphism from some abstract K to this group of QCAs, and if you, for some values, for some group elements, you get a non-zero value of GNVW index, that's already sort of anomaly. Because a QCAs cannot be, actually, with non-trivial GNVW index, cannot be localized even to a half line without breaking unitarity or locality. So, now I want to say that abstractions are coming from some degree cohomology class, whatever. But here, there's no cohomology. It's just, or if you wish, like a degree 1 abstraction. Homomorphism itself can be, without further computation, can be anomalous because some group elements map to QCAs with non-trivial GNVW index. So just for simplicity, for this talk, I'm going to read symmetries which act by circuits, not by arbitrary QCAs. And that's not really unsatisfactory. Indicates some problem with this homotopy picture. There is some refinement is needed, but let me continue with this assumption that symmetry is going to act by circuits. Okay, so now we want to construct a crossed module, or two group, for 1D lattice system. How do we do that? Well, we need a pair of groups and a homomorphism between them, and also an action of G on H. That's the rest. Okay, so let circuits localized gamma be made of circuits which act trivially on all observables supported outside of some neighborhood of gamma. So in this QCA business, everything localization cannot be strict. It's kind of fuzzy because we have a finite range condition. So when I say circuits localized on gamma, it just means something which is approximately localized on gamma in the sense that they act trivial on observables outside of some neighborhood of my subset. Okay, for example, if you look at 0 points, point 0 on the lattice, then circ 0 is just automorphisms which act trivial on anything out far from 0. And it's well known that such things are just called just conjugation with the local observable, well, unitary local observable. And I'll introduce some notation. Let's call this curly U is going to be the group of unitary local observables. It's a subset of the algebra of all local observables. Okay, so, and I'll have notation for, for conjugation with local observables called addu, adjoint action. So, okay, which two group are we going to consider? I propose look this one. Our H is going to be unitary local observables. Our G is going to be circuits localized on the positive half line in the approximate sense. And the map is going to be simply adjoint action. That is, if you for a unitary, you can attach, its conjugation with it. It's an example of a circuit. And what about the action of G on H? Well, of course, conjugating a local observable, unitary local observable with a circuit gives another unitary local observable. Okay, so we defined our crossed module or two group. Does this make sense? Okay, so now what about homotopy groups of this crossed module? That's first thing. Well, kernel of this map, adjoint map, is simply U1. That's clear. That's the only thing which commutes, which just trivial maps on observables. So pi2 is U1 as expected. What about G0? Well, G0 is a bit funny. So it's a group of circuits localized on a positive half line, modular circuits localized at 0. Localization again is approximate. That's not exactly what we expect normally. That you usually wouldn't call that a symmetry group of 1 plus 1 dimensional system. However, any symmetry in the normal sense does give you a homomorphism from K to this G naught, to this pi1 of this cross module. Indeed, suppose you have an action by circuits. You can truncate any circuit to a half line simply by throwing away all gates which are do not live on this half line. That gives you a unitary, therefore we get a homomorphism from K to circuits on the half line, mod circuits at 0. Why mod circuits at 0? Well, because even when I do this truncation thing, something which is a homomorphism is not going to stay homomorphism, but it will be homomorphism up to things localized at the origin. So that's why we get homomorphism to this quotient group. Okay, that's good. So we do get any action does give rise to homomorphism from K to our pi1 of our 2 group. Finally, we may have some Postnikov invariant. Okay. And I already explained how to extract this Postnikov class for any two crossed module. So you can just apply it to this particular crossed module and specify what you get and pull it back to K, and you get some class in H3 K of U1. So this is actually not something new. This is just a 't Hooft anomaly constructed by Nayak and Else in 2014. So that actually was the motivation for this whole approach to reinterpret Nayak and Else in more like homotopy theoretic terms. So at least in one dimension that we're good, we can reinterpret the anomaly in terms of in homotopy theoretic terms, an abstraction for promoting some homomorphism of groups to a homomorphism of 2 groups. Now things become more interesting when you go to 2 spatial dimensions. How do we model 3 groups, in other words? Okay, in that case, unlike in the case of 2 groups, there is more than one group theoretic model, but it turns out that the one which is physically most natural exists in the literature called the crossed square of groups. So what is it? Well, you have it's actually have 4 groups. All these arrows are homomorphisms. As usual, this diagram commutes. That if you do this, apply homomorphism this way, but on this one, it's the same as this and this. And there is some additional data. First of all, there's an action of this P on all these other 3 groups. And then there is some weird map from M times N to L. And some list of pretty complicated identities, which all these guys satisfy. Now, you don't actually have to remember these identities. One can recover them when you're on an island by thinking about a special case. Just take P to be any group, take M and N to be 2 normal subgroups, and take L to be the intersection. And then all the maps become kind of obvious. And the least obvious one is eta. That simply becomes the commutator. If you take, if you look at the commutator of two subgroups, like two elements of two normal subgroups, it's going to lie the intersection. So that's our eta. Now, of course, I'm not saying that general cross square is like that. I'm just saying that the identities for all these maps can be figured out by looking at the special case. Okay, looks pretty complicated, but one extracted three group out of it, and it goes in. These are other two papers by Condorcet from 1984 and 2003, which explain how to do that. So first you form a complex of groups, non-abelian groups like this, where here is semi-direct product, and look at its homology groups. And its homology groups are the homotopy groups of the three group. So for example, what is pi 3? That's the easy one. Pi 3 is just the kernel of this left arrow. What's pi 1? Well, it's a kernel of the right arrow. It's it's the p modulo the image of this guy in p. And then the pi 2 is just the middle homology of this guy. That is the kernel of the right arrow modulo the image of the left arrow. Okay. Well, Postnik invariants are more complicated. Anyway, so how do we get that from a lattice model? Okay, I need to first of all exhibit for you P, L, M, and N. So here's a picture of a two-dimensional, of a plane. So I'm going to draw the lattice. So I pick a random, I pick some half plane, and let P to be circuits localized on the positive, on this half plane. What about M? Well, M is going to be circuits localized at this half coordinate axis. And N is everything localized on the lower half coordinate axis. Okay. So I'm going to say localized again in the fuzzy sense. They localize in some neighborhood of this half line. So you can check these for all form groups. And it's easy to see that also, there's an obvious way, everything localized on this in the neighborhood of this half line. Of course, localized also in this fuzzy sense on the half plane, right? So there's like obvious, M is actually a subgroup of P.
So L is the intersection of M and N, but M and N don't intersect.
So L is not intersection because here I keep information about the phase of the observable.
Okay.
Like if I look at the adjoint map from U to automorphisms, then yes, L is simply the intersection of M and N. However, I choose define L differently. I want to keep the information about the phase of the local observable, so it's actually not a subgroup. It just maps to both M and N. Okay, and already from this you can see what pi 3, pi 2, and pi 1 are. So pi 3 is simply U1. That's simply the kernel of the map from L to M and N. The only thing which maps trivially is scalars. Pi 2 is 0, and pi 1 is circuits on the positive plane modular circuits at the on this divide on the vertical line. Now, why did pi 2 vanish? Well, this is a lattice system without Gauss law constraints. Actually, we do expect high form symmetries, like non-trivial ones, to appear only in gauge theories. Now, okay, so that's all I want to say about homotopy groups, but there is, of course, some Postnikov invariant in this case. So since pi 2 vanishes, that's actually the case when only have only two non-trivial homotopy groups. It should be a very simple Postnikov invariant. Well, simple in the sense that there's only one of them. Degree 4 class of BG0 with coefficients in G2, which is U1. Well, to write this formula for this class actually very, very non-trivial. That's the achievement of this paper of Condorcet. Horrible formula. Kabago and Shirley derived the same formula for the class gamma without using this, high polluting math. Now there's some subtlety. Let me just, well, okay, so there's some subtlety here. So suppose I have an action of a group on a lattice system in a normal sense, that is by homomorphism from K to QCAs on the whole plane. Okay, so let's even assume it goes to circuits as before, as in the one-dimensional case. is actually not enough to get an action in this homologous theoretic sense. Because if you just truncate circuits to the half plane, then you get homomorphisms from circuits on the half plane to QCAs at x equals on the line. But our homotopy group, phi 1, is actually circuits on the half plane modulo circuits on the line. So this group on the left is actually quotient of this group on the right. To lift that, to one to the other, you actually need some structure needs to vanish. It's also kind of anomaly. It's for system of qubits, for example, it's a degree 2 class of K with capacities in Z. That actually doesn't really fit into our homotopy theoretic picture either. So it's kind of special to lattice models. There's no analog in QFT, but it's annoying that I cannot fit it. So I'm not going to resolve this here. Let me just say that what to do in the case of lattice gauge theories where there are non-trivial one-form symmetries. So in that case, you need to restrict to the algebra of local observables, which are commute with Gauss law constraints, gauge invariant observables. So suppose you look at Z2 gauge theory. Then you have a Gauss law constraint for your vertex. So you just for your vertex you have take the product of all x Paulis for that vertex, for all edges entering this vertex, and that gives you a Gauss law constraint. And you have one such guy for each vertex. So how do we now define, in this case, three groups? Well, you define the same way. So you just still, look at the same picture with a head, except you only use gauge invariant circuits and gauge invariant observables. Let's see if it gives you the right answer. Well, for example, let's look at, in case of Z2 one-form symmetry, Z2 gauge theory, you expect a one-form symmetry, which is Z2. Can we see that? Well, pi 2 of the 3 group should be represented by what? By kernel of some map. Now, what does it look like? Well, actually, this is, physically it should be a string of Pauli x's along some path on the dual lattice. And I choose it to be, let me pick the one which runs along the vertical line. So how does it fit into our picture? Well, what you do, you split this string, which is actually induces a trivial automorphism of algebra of local observable, gauge invariant observables. So that's good because actually it should induce trivial automorphism. If you remember, pi 2 was what is pi 2? It's a pair of things living on this half line and that half line, which map together to something trivial in this automorphism acting on the half plane. What's the map? Well, the map is just like a product of automorphism of symmetry here and symmetry there. So you actually do want to get something which lives on the whole line but acts trivially. So that's what this thing is, right? It's a concrete string of x's which actually induces trivial automorphism local observables. But if you split it into two things living on the vertical, on two half lines, actually becomes non-trivial. Namely, it flips the sign of plaquette, which lives here marked with a blue dot. So that's an element of pi 2. And you can check it's a non-trivial element of pi 2 because you cannot affect, there's no local observable conjugating with which gives you this effect, flipping the sign of plaquette here and nothing else. So it's an element of pi 2. Okay. Some question there. Let's see the chat.
I'm sorry, what do you mean by flipping the sign of the plaquette?
So if you look at product of Z's, right?
Is it a Z2 gauge theory?
Z2 gauge theory. So
you flip the sign of the product of Z's around the plaquette?
yes.
Okay.
So this is an element of the gauge invariant algebra gauge invariant local observables, and this half string flips that, right? And the other half string also flips that. And that's actually the only effect of these two half strings, right? It doesn't do anything to anything else, which is gauge invariant. And if you take product, then does nothing at all. So that means it's the kernel of the map. Okay, so now what does it mean to say that the Z2 is a one-form symmetry? Well, it's just the same as before, basically, except you say that a group K X by one form symmetries, if you give the homomorphism from K to group of one form symmetries, which from my point of view is a pi 2 of this classifying space. Okay, what do I mean by anomaly of one form symmetry? Well, I can try to leave this to so basically just strip off the the lowest rung of the Postnikov tower, just left with now with the second and higher levels. And then they say, well, can you lift this map to pi 2 to the actual map of spaces? And again, in general is an abstraction. And abstraction in this case is degree 4 class of what? Of the space on the lowest level now. Well, after throwing away, the lowest level now is this one with values in, two form symmetries. Now, this is some horrible thing at first sight, but there is a result that actually is the same as a group of quadratic functions on G1 with values in G2. That's the result of Eilenberg and MacLean. And that actually is very easy to see in the special case when G2 is U1. Because what is this group? From the TQFT point of view, that's the group H4 of the blah, 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 is just simply the group of topological actions for two-form gauge field with values in G1. And we know what all that is. It's a quadratic function of this two-form gauge field. Okay, so we're supposed to, from our three group, we're supposed to be able to construct a quadratic function on pi 2 with values in pi 1. And it's very easy. It's just a value of this additional datum, which had this map from m times n to L. You just evaluate this map and take the inverse. So, and if you remember what this is, it's just the commutator of two half strings. So the commutator map on the two half strings gives you this quadratic function. The fact that it's quadratic follows from some non-trivial computation, but it's guaranteed by the structure of the three group. Of course, in the case of this vanilla gauge theory, it becomes trivial because the two half strings do commute, they're just made of x's. But if you modify the Gauss constraints, you do get non-trivial anomaly, which some example in my paper with Lev Spirinenko. So from the QFT perspective, this function encodes a braided tensor category of defects. Okay, and it's very straightforward to just compute it from the if you know the three group structure.
Okay.
It's non-trivial that you get quadratic function, by the way, independent of any choices. Yeah.
Can I ask a question?
Yes.
So suppose that we have a Z2 one-form symmetry, which is anomalous, that corresponds to semia. So in this case, I guess there is no truncation of the line operator, which is gauge invariant.
Yeah, it's the same issue basically that I already alluded to. So all these issues are related. So remember that I had this issue before even when I discussed no Gauss laws. Let's see.
So you say that anomaly in this case is characterized by the absence of the truncated symmetry operator?
Yes. Yeah, there's some extra anomalies. For example, yeah. So there is this. There's this. For example, this anomaly, right? We discussed in the slide. Also doesn't have a homomorphic interpretation yet. So it's the same issue, splitting of the line. It's the same thing right here, except here's an H2.
I see.
Yeah, so, and in fact, GNV double index is also an example of that. So all these examples have to do with something happening in one dimension, which is not captured by this homomorphic interpretation.
Okay, thank you.
Okay, anyway, so I'm done here. Let me just again show this the summary. So that anomalies come from the mixing of zero form symmetry and in the usual QFT sense. In the usual QFT sense, just mixing of zero form symmetries and trivial U1 D form symmetry. And high form symmetries themselves, just an aspect of locality. Just the fact you can talk about symmetries localized on regions gives rise to higher form symmetry. That's it. In operator language. Now, another thing, which is that high form symmetries and anomalies are just kinematic. They don't depend on the Hamiltonian, only the Gauss law constraints. So in practice, I want to say the following thing: like, how does Hamiltonian actually enter the picture? Like, if you say in two dimensions clearer. So you do want to say that P is made of things which preserves the Hamiltonian in some sense, right? But you don't need to do this for M and N. So you can see there's an example of these two gauge theories. So I would say that one form symmetry and high form symmetry just something which reflects structure of Gauss law constraints. Well, and finally, okay, I stressed that this is not the final picture, but to capture all of anomalies we see on the lattice, it's definitely truly going to need to use homotopy theory. Maybe not list the most elementary one, which I used here, but some gadgets from homotopy theory. Somehow homotopy theory captures both locality constraints. Okay, so that's all. Sorry for running over time.
Okay, thanks a lot. Are there more questions?
Hi, yeah. So you mentioned that you can't describe these invariants that involve QCA indices. And then you said that there is no analog of that in QFT. I kind of have to push back on that statement. The invariants that involve QCA indices are very much like analogous to the beyond cohomology anomalies that you see in QFT. So that's why it's kind of concerning to me that you can't describe these things in your formalism.
Yeah, well, it's true. So as I say, this formalism is not the final word. Basically, it's an illustration that can get some of the anomalies using homotopy theory. And another thing is that I emphasize that actually it's not necessary to talk at all about non-local observables. Oh, okay. So everything is formed in terms of local observables. And I think that lessons are going to apply in general, even in the correct approach, which is not completely correct. Yeah. So I think everything should be described in terms of algebraic approach, which only has local observables in it. But what sort of homotopy theory gadget is needed for that is not completely clear yet. And I think if you use correct homotopy gadget, you will get all these higher form symmetries and anomalies correctly. Yes.
Nadi?
Yeah, to what extent does this give you constraints on the IR dynamics?
So one can show, well, it's not clear with the two-dimensional, for example, anomaly. It's known for the one-dimensional anomaly. One-dimensional anomaly, one can show that
One dimension, you mean 1 plus 1?
yeah, 1 plus 1. So 1 plus 1 dimensions, the implications are well known. So there's so for example, a paper with Nikita Sapenko, which I wrote a couple of years ago, which explains that if you have a gapped Hamiltonian, if you have Hamiltonian with a symmetry, which is invariant of the symmetry with non-trivial anomaly, so it cannot have a gapped invariant ground state. So in higher dimensions, we only know some weaker statements, namely that you cannot have, say, short-range entangled states invariant under symmetry if the symmetry has non-trivial anomaly. But to understand dynamical statements, you need to understand better, the dynamics. This is almost a kinematic, right? So they do give constraints on states, but what sort of states? You need to understand what makes ground states of local Hamiltonians special. We do understand it in one dimension, but not in 2 dimensions.
I see. And in quantum mechanics, does it tell you the same thing or not?
Well, quantum mechanics kind of doesn't really fit into this picture because they say the anomaly is only visible once you go to level of Hilbert space.
Yuan?
Hi, Anton. I have a quick question about your setting. So it's like you impose your Gauss constraint and then solve for the higher form symmetry. But in your example, your one form symmetry is simply the product of the vertex term on the half plane. So is it always the case that given the Gauss law, you just multiply on the half plane and give you the one form symmetry?
Okay, so one form symmetry is not the Gauss law, it's the different things. So one form symmetry is an element of pi2, right? And arises in the following way. So first you act by Gauss law constraint on some region, say half plane. Then that gives you some circuits on the boundary of that region. If it does that, suppose it does give you something on the boundary of that region. For example, if you have a system with charged fermions, you also have Gauss laws, right? But if you act with the Gauss laws on the half plane, you're not going to get something localized on some circuit localized on the boundary. If you don't have a charged matter, then you will. And then here you also have to do further split of this circuit on the boundary, which by definition acts trivially, by the way, on gauge invariant observables. Now we have to split it into two half-line circuits. So from our point of view, one-form symmetry is this pair of half-line circuits.
Okay, so the symmetry group is always smaller than the gauge group.
Um, let's see. Yes, I would say that. Yeah.
Okay, thank you.
Okay, Zahand.
I have a question related to another question I asked, maybe also Dominic asked, that the fact that you're only focusing on circuit, does it mean that by hand you're throwing out symmetries with beyond cohomology anomalies? For instance, if you go to higher dimension or 1D system like fermionic, Majorana
No,
translation.
yeah, I agree. So this is, like I say, this is like just something, it should be more general construction, which involves QCAs, which are not circuits. I don't know how to do that. So you're invited to explore that. Yeah, and then you'll probably will get beyond cohomology anomalies.
I see. So this resolves the fact that if you have only in your higher group, if you have only two non-zero entries, then it's always cohomological type because it's Postnikov class, as you said before.
Yeah.
Yeah, Argo.
Yeah, my question was about higher group symmetries in QFT. So we know that there are examples where QFT has higher group symmetries. In that context, how should I think of their anomalies? Because it's already a higher group. There's no obstruction, there's no other lift to think of, right? So how should I think of the anomalies of, let's say, a two-group symmetry, two-group global symmetry?
No, in that case, there's an anomaly. I mean, it's just saying, suppose when I say there is some, let's say, one-form symmetry, right, in 2 plus 1 dimensions. Okay, that means there's a pi 2. Okay, but there could be Postnikov class. It's just suppose that just ignore zero-form symmetry. You just now have pi 2 and pi 3. You have one-form and a two-form symmetry. Anomaly for the one-form symmetry is simply the failure of the classifying space to be a product of zero form, one-form and two-form symmetry classifying spaces.
Maybe I didn't explain clearly. So I was just thinking of non-trivial two-group symmetry, so not a split two-group. I just have a non-trivial Postnikov, maybe more than it could be, higher group, even more higher groups. They could have an anomaly, and there would be an inflow theory in the QFT language.
Let's see. So okay, let's decide which dimensions are we in. If we're in 1 plus 1 dimensions, there's nothing except there's something higher than pi 2.
Yeah, maybe I was thinking of like arbitrarily large dimensions, maybe 2 plus 1 or 3 plus 1.
Well, suppose you have 2 plus 1. In that
Okay,
case,
sure. Yeah.
the leading Postnikov is not usually called anomaly. Okay. However, sometimes it is called anomaly. Think on the context of TQFT. So when you have some action by usually I think it's called fractionalization class. So that guy can also be thought of as an anomaly.
Mhm. Is
So
it the H2 class?
it's H2, maybe not. Okay, so there's a class in H3 there as well.
Right.
And that
Yeah, it's
class,
often called an anomaly.
yeah, so it's an anomaly of sorts, even though within QFT context you usually don't think about it as an anomaly, but it is. I would say it's also an anomaly. So for me, all these
I
Postnikov
see.
invariants are all anomalies, but the top one, the one so like the one which you usually encounter in QFT is the one which ignores everything except the bottom, there is zero form symmetry, and the top one, which is deform symmetry. Yeah, deform symmetry. So that's the usual anomaly. But in general, when there are higher form symmetries in between, there are also like lower anomalies, if you wish.
But you also have a beyond cohomology anomalies, which seem like kind of different, right? Because there's still like invertible anomalies, whereas what you're talking about is like somehow a non-invertible anomaly because like it's resolved by non-invertible theory.
I'm not sure what I mean by non-invertible anomaly. I mean, like for me, anomaly, say the degree 3 class of a G cross braided category is an invertible anomaly. So
Well, normally
it's
what happens when you have this non-trivial H3 is that you have to have like a non-trivial, non-invertible topological phase in the bulk or something.
okay, but for me, I call it invertible because everything from in terms of groups. So
Can I take you backwards? I need to understand something. In what sense is the fractionalization class an anomaly?
okay, let's see which one.
Or maybe I should start easier. What is it an anomaly in?
To a certain extent, a matter of terminology, but somehow the point is when you have when you have anomaly, you have to do something non-trivial when you gauge, the say zero form symmetry. So you have to involve one form symmetry as well. So
So what is it an anomaly in?
okay. So you have some action of a group in a naive sense, in a zero form symmetry sense. So
Yes.
there's homomorphism from abstract group to your group of zero form symmetries. So it's an anomaly in zero form symmetry, in your what you call zero form symmetry of some sort. And anomaly in the sense that you have to involve one form symmetries when you try gauging the zero form symmetry.
I mean, so if I start, say, U1 level 4, and I couple it to a zero form U1 symmetry, electromagnetism, and I have some fractionalization class, I can gauge the U1. Not only can I do it, nature has already done it for me. And
I
there's
think
nothing wrong.
I think there's a terminology issue. I think what Anton was saying is symmetry fractionalization is it's an H3 class, and sometimes people call it an obstruction to symmetry fractionalization.
No, I think he said H2.
No, I meant H3. Yeah.
I think fractionalization class means what U1 charges, what zero form U1 charges you assign to the lines. I think that's what people usually call fractionalization class.
Okay, so that was then just me misremembering what terminology is.
I think I've been arguing about terminology for the last several months with people, so maybe somebody who's more knowledgeable about that should correct me.
I think people call that an obstruction to symmetry fractionalization, this H3 class. Just to comment, like that H3 class doesn't lead to any obstructions on RG flows. So you could have like this two group structure with this H3 class being non-trivial and have a trivial symmetric gapped phase.
Okay. Yeah.
But
So anomalies, it's kind of common now, like to observe that what we might want to call anomaly is not necessarily obstruction to gauging. For example, this H2 anomaly on the lattice, which we discussed in paper of Shirley, Levin, Zhang, G, that doesn't lead to actual obstruction to gauging, even though it is sort of anomaly.
It doesn't lead to obstruction to trivial ground state. It is an obstruction to gauging on the lattice.
Yeah, sorry. Yeah, it's true. Anyway, so there's some distinction between anomalies, gauging, obstruction to gauging. So yeah, so
In
I
fact,
would
in
say
that paper, they called it specifically non-anomalous, right? They said that's just an obstruction to on-siting. It's not actually an anomaly.
Well, okay, that's now is another word on citability. So there's more proliferation of terminology. So I don't know what to call this, but the point is that the usual anomaly is a aspect of high form symmetry. Whether you want to call other higher aspects of high form symmetry, some mixing between different high group P form symmetry groups and anomalies, up to you. So
Actually, I had a follow-up question to Arco's question. So let me be in 1+1D and have something like Z2 gauge theory. So there's a Z2 zero form symmetry. There's a Z2 one form symmetry, which is different and not related to your universal U1.
yeah.
And in that theory, there's a mixed 't Hooft anomaly between the Z2 zero form and Z2 one form symmetries in this 1+1D Z2 gauge theory. In such an instance, can you have that mixed anomaly be captured by the framework you were discussing?
Okay, what is the theory again?
Yeah, for example, maybe you could write the action as I have some compact scalar phi, I have some U gauge field A, and the action would be like I over pi integral phi dA. So make a 2D Digraph-Witten theory
Okay.
with
I need to think about this. Yeah.
I see. Yeah, but more broadly, if I have a D-form symmetry for D-dimensional space, and that itself has an anomaly, a 't anomaly. Yeah, I just wonder if that could arise in the way you've been talking about things.
Sorry, Sal, did you really mean Digraph-Witten or just a Z2 gauge theory?
I really meant Z2 gauge theory, but sometimes I see people call Digraph-Witten even when the twist is trivial, so I thought maybe that word would be helpful.
Ah,
Yeah, I don't know, like whether I know I haven't really thought about the case when the D-form symmetry itself is not just the canonical U1, but there's some other stuff.
Uh-huh.
But naively, I would think that I don't see anything wrong with having, say, a group structure which is this high D-form symmetry, which is not just a product of the two things, but some extension maybe. So that might be thought of as any mixing. Say, in a non-trivial group structure of high-form symmetry probably can be thought of as some sort of anomaly. I don't know. I need to check that in some examples.
I see. All right, thanks.
Sorry, a related question / comment. If you are in 2+1D, and if we have a 0 form and a 1 form symmetry, so we have a non-trivial Postnikov class that is in H3. This doesn't prevent you from gauging, doesn't prevent you from having a trivial gap phase. But on top of that, there might be also an H4 class of the classifying space of the 2 group. And that is an anomaly for the full 2 group structure.
Yeah.
So is that captured in your?
Well, it's there automatically. The 3 group is canonically constructed. Well, almost canonically constructed. So you can extract on it all the homotopy theoretic information you like, in particular that one.
Okay.
Okay, I think we will close the session. I have lots of questions. Thanks a lot again, Anton. And
Thank you.
next week